So today I'm going to talk about the interest in CMS, about supporting and using heterogeneous resources. I'll begin talking a little bit about the CMS experiment and the CMS Submission Infrastructure group. I'll explain why we are interested in using GPUs. I'll talk about how we allocate and use them, and then I'll show some tests we ran, and I'll finally conclude my talk talking about accounting and drawing some conclusions. So I think most of you are familiar with the CMS experiment. It's one of the 4 high energy physics general purpose experiment that is analyzing the data collected at the Large Hadron Collider at CERN. And data is stored, distributed, reconstructed, and analyzed, comparing it to simulated Monte Carlo data. And current projection foreseen a 4-time gap in the CPU needs, considering a flat funding schema, starting by 2027, when the high luminosity LHC era will begin. And this is including the natural evolution of the computing power. So this is already including the CPU will and processor will improve. And for the computational needs, CMS uses the WLCG, the worldwide LHC computing grid resources, which is a global collaboration of 170 computing centers, and the access to those centers is based on pledges. So sites, each one of those sites decides to pledge a set of resources to one of the experiment. Those resources we can consider that are always there and always running for the reserve for that experiment. And those are mostly homogeneous resources. There is a VO card, a set of requirements that sites need to fulfill. And we also began to exploit HPC resources as well recently. This is driven by those needs in computational needs, and the need to search for new ways to account for our resource for computational needs. And these are very different resources compared to the standard WLCG grid. First, the access is allocation based, so experiments are like CMS are given an allocation so you're basically paying for your resources as you use those resources, and those resources are not always there. You are assigned to those resources based on the availability. And the other aspect of HPC is that these are heterogeneous resources. There are different architecture. There are sometimes resources that are network segregated. And the interest of this talk, there are many resources that have GPUs available. And within the CMS experiment, the Submission Infrastructure group organizes the HTCondor operations, which is the technology CMS uses to access all of these resources. And in particular, we organized an HTCondor and GlideinWMS operation experiment. GlideinWMS is the tool used to acquire the resources through a pilot model. And in particular, the bulk of the resources is concentrated in what we call the global pool, which is the infrastructure where the reconstruction, simulation, analysis of physics data take place. Other aspects the submission infrastructure group take care of are communicating priorities, development priorities to the GlideinWMS HTCondor group. And for that reason, we hold regular meetings with the development communities, those development communities, to communicate our feature requests, to communicate operational limitation and future scale requirements. And as you can see, the number of cores adopted in the global pool have been constantly increasing in the past 5 years, and we expect this to increase even more in the next years. The submission infrastructure is even more complex than the global pool itself. We have different pool. Actually, we have a pool dedicated to CERN resources. We have a pool, the HEP Cloud pool, dedicated to HPCs in the US, which is operated at Fermilab. We have a pool for volunteer resources. We have other external pool. We have 2 sets of workload manager. One is CRAB, which is used by individual physicists, more than 400 physicists, and one is WMS, which is the tool used for the central processing. We have around 50 schedulers and a redundant high availability infrastructure where all the central component, like the 3 negotiators that we run for the global pool, are replicated at Fermilab. And those resources, the one in green, we have different type of resources, and the main one are the WLCG resources and those resources are acquired through the GlideinWMS tool, which sends pilot job. So whose role is to connect to the central manager in the global pool and create a machine slots to be ready to be used by the different schedulers, by the different user jobs in the schedulers. And so basically those jobs create a machine and then jobs run inside those. It's a job inside job mechanism. And our interest for GPU is starting because the availability of graphic accelerators increasing, and not only on HPCs, but also among traditional WLCG resources. And we want to be ready to run also a substantial part of our processing at HPCs, because we expect a high fraction of computing power will become from HPC, which is a shift driven mostly by funding agencies, and at these places we have a lot of GPUs available, and we want to profit for them. And for that reason, the group in charge of the CMSSW framework, which is the framework that orchestrates the data processing in CMS, have been working hard to enable use of GPUs in our framework, and which is now able to offload the computation to GPU accelerator. There are two modes to offload the computation. One is in process, where accelerator present on the same node are used. So basically, everything is inside the same process. And this is the focus of this talk, but there's also work ongoing to enable external offload, which means there is an external process that coordinates and is like an event process, and process events coming from other CMS run processes. So we have already a farm at CERN, the high-level trigger farm, which is featuring CPUs and GPUs, and we plan to use this for the online calculations, so the calculation that are executed while the data is taken. And the plan is to use up to 25% of the reconstruction on GPUs. And the good thing is that the offline data processing framework and the algorithms are the same used for the online, and we can reuse those also for offline computation. And one key aspect of the framework, of the CMSSW framework, is that it is able to dynamically use the GPUs when they are available, which means that it's able to use all the computation power that it finds on the worker node being these CPUs or GPUs. So it's not a dedicated GPU workload. It's able to use both CPUs and GPUs in parallel. And this is something I will come back in a few slides later on. NVIDIA CUDA is used as a language, and there are plans to use performance portability library to enable other languages. I'll focus more on how the resources are allocated and how the workload is scheduled in the next slide, which is the key business of the submission infrastructure group. The pilot jobs that GlideinWMS sends needs to be configured, and typically for CPU workload, we use 8-core partitionable pilots with, and it's also possible to use whole node pilots where a pilot is started on a worker node and grabs all the CPUs and GPUs available on that worker node. And we need to append GPU resources to those slots, to those computation, to those type of configuration. And two ways to do this are: one, to create a dedicated slot for GPUs and keep the CPUs remaining in another slot, or use the whole node configuration again and append the GPU to the same slot. We are currently using a mix depending on the site admin preferences, and so either a whole node configuration or 8 CPUs plus 1 GPUs. And there is a flexibility versus efficiency trade-off, in the sense that the whole node configuration is more flexible. We can run diverse type of jobs. We can run single jobs that run one CPU and one that requires one CPU and one GPU, and the rest dedicated to a 30 CPU job if needed, or we can partition those as needed, basically. While the 8-core 1 GPU is a little bit more rigid, but it's the trade is in the efficiency, meaning that it is less likely that the slot will become fragmented. Once you have the resources, the next thing to do is the matchmaking, and we have worked with our colleagues in the physics and the workload management development to define a set of matchmaking attribute. There is a main switch which we use to determine if a job will require CPUs, GPUs, and we were asked to accommodate for the use case where payload use the GPU is if it is available. So basically, it's like, and this is something we'll discuss a bit more in the later slide. There are also mandatory attributes which have been required in the memory, the CUDA capability. We ran also a script at the beginning of the pilot to determine a list of compatible runtime, but trying to try to use the driver shipped with this CMS framework in place of the system drivers. And then there are a list of monitoring and debug attributes. We also performed some tests, where I say I mean submission infrastructure, to check if these matchmaking algorithms were working. We tested this using jobs pointing to all sites available that share GPUs. And to measure the performances, we executed a simple script that was running a matrix multiplication, a 10,000 lines times 10,000 line random matrix multiplication 10,000 times. So 10,000 of those matrices were multiplied, and we recorded the execution time as a metric to correlate performance as a function of the GPU model. So we run those tests. There are some sites that are sharing GPUs. This is the list. And this is kind of an interesting result, at least is something probably obvious to expert, but something that was a little bit surprising for me was that there is a 10-time difference in the performances between the most efficient type of GPU and the least efficient one. And this is a key aspect because we normally have run under the assumption that all the resources are the same, and our workload management rely on this assumption, and we also rely on this assumption for scheduling. So it's something we need to consider going forward. We run also a regular scan of the global pool resources for GPUs by submitting pilots that run the HTCondor GPU discovery tool and find out a set of characteristics that are shown in a Grafana chart. And those resources are opportunistic in nature. For now, we don't have pledges. We have sites that voluntarily, regular WLCG sites that voluntarily are adding GPUs to their CMS pool of resources. And once you grab those resources, you also need to use them efficiently. And typically, the CPU efficiency in the HTCondor Global Pool is between 90 and 95%. And we want to keep it that way also using GPUs. And, and in this case, for GPU, the site policies matters a lot, and we have been receiving feedback of site that wants to prioritize the use of GPU over the CPUs on their node. So when there is when we grab a GPU slot with a pilot, they want us to run a GPU workload because GPU is the most expensive resources on that node, and they want to maximize the use of that resource. And then after that, we can saturate the CPU part is possible. But of course, when the GPU jobs running on that slot are done, we want to be able to run more GPU job, and we want to be able to vacate the CPU's jobs running on that slot if necessary, if this is required to match new GPU job. And for that reason, we are considering preemption for the CPU part, which would be a first time for submission infrastructure, but it's something that we need to be considering in case to maximize the efficiency.
Sorry, Marco, you have 2 minutes left.
2 minutes, you said? Okay. Another thing we plan to keep doing is to remove pilot that are idle for sites if necessary, like we do for CPUs. There are a couple of open questions. One is about benchmarking and accounting. Benchmarking, of course, is important, is already used. We have the HEP-spec 06 that is currently used for CPUs, and it's used for pledge definition for resource acquisition, so for sites to decide which resource to buy. Is a measure on how a CPU is able to efficiently process high energy physics workload. GPUs is not included in the current benchmark. There are plans to use GPU to include it in the next iteration of the benchmark, but is not already there. And one of the reasons we need that is to be able to determine how well a CPU, a site will be able to process our job and how fast, because of what I was saying before of the high variability in the GPU resources and how fast they can process our resources, our jobs. And for the accounting, we plan to use information that are already available, and for example, GPU time or other HTCondor attributes that are available. Few considerations about the use GPU if available. So the two questions are basically how to treat user job that these are not requiring for a 0, 1, 2 number of GPU, but they are willing to use GPU if they are available. And the question is, should we treat those, should we trigger GPU pilot if those jobs are present? Should we do, what should we do in terms of priority once we have a pilot? We have already been doing something flexible, flexible matchmaking for CPUs, which we call resizable job. It's something we can consider, we will consider in the future, but for now we are focused on the simple use case where the request GPU is a constant number. Something, so this is something for the future. And I guess the conclusion, really quick, we have been, the Submission Infrastructure group has been working for making a GPU resource available and to other groups in CMS, and we are ready to coordinate with the software and workload management team for realistic workload submission. And there are a couple of to-dos to assess, which are benchmarking and the use GPU if available. And of course, we thanks the HTCondor development team and the continuous support they give us to us and to our group. And thanks. That's all.